Aloha, I'm Roger Brewer with the Hawaii Department of Health. You're listening to a recording of a webinar entitled Dungeons, Dragons, Pica Houses, and the Need for Alternative Vapor Intrusion Screening Tools. This webinar was originally given on February 18th, 2015. This webinar overviews a paper that was published by myself and Josh Nagashima in our UST office in December of 2014 entitled Estimation of Generic Subslab Attenuation Factors for Vapor Intrusion Investigations. We had three co-authors for the paper. First, we wanted to get someone really good in risk assessment, toxicology background, vapor intrusion. So we recruited Dr. Mark Rigby with Parsons Environmental, also with UC Santa Barbara. We also wanted to get some people with a lot of field experience to co-author the paper. So we got Martin Smith with Cox, Colvin and Associates, a lot of vapor intrusion field investigation experience, and also they're the makers of vapor pens, which are getting very popular. And we got Harry O'Neill with Beacon Environmental Services. And Harry, like Martin, has a lot of field experience, especially in passive soil gas sampling. Now the paper, just to set up front, we review two different US EPA methods for estimation of default soil gas to indoor air attenuation factors, focusing on subslab attenuation factors. We've been working on this paper for about 2 years. Before it was published in December 2014. In reality, for 10 or 15 years before that. So we discussed the paper and manuscript and ideas with a lot of vapor intrusion experts across the mainland, including in US EPA and various state agencies. And we gave a presentation on the paper at the Battelle Conference in Monterey, California in May 2014, prior to completion of the paper. And there were a number of people that reviewed draft manuscripts of the paper, both regulators and private consultants. The paper went through an 8-month peer review with groundwater monitoring and remediation, where we had it published, and again finally published on December 14th. So there was a lot of time spent on this paper, a lot of people involved. There are only 5 authors listed. In reality, there are dozens of authors behind this. Just a quick overview of vapor intrusion. And again, we're focusing on subslab attenuation factors, but vapor intrusion really isn't that complicated. It's when a building is under pressure, as you see in the diagram on the lower left, either due to wind effects or especially heating. And if there are gaps and cracks in the floor and the subsurface vapors immediately underneath the slab or even in a crawl space could be pulled up through these gaps and impact indoor air. So the vapors get pulled up through the floor, mixed with indoor air, and this is called attenuation. So you get a reduction in the final concentration of VOCs compared to what was in the subslab vapors. So this subslab attenuation factor is really a critical parameter for screening for vapor intrusion concerns at sites. Again, 2 different methods have been developed, published by US EPA. We're going to review both those here. So the subslab attenuation factor it's just you can think of it as the dilution of subsurface vapors as they mix with indoor air. So the first method we reviewed, this is the original method in the US EPA's vapor intrusion guidance. The subslab attenuation factor is simply estimated as the ratio of the vapor entry rate to the indoor air exchange rate. And both of these are measured in liters per minute. Some example subslab soil gas attenuation factors from California, the Department of Toxic Substance Control in their 2011 guidance. We rounded this off some, but their default subslab attenuation factor using this method is based on a default vapor entry rate of 5 liters per minute and a default indoor air exchange rate equivalent of 2,000 liters per minute. This is based on an assumed house volume of 244 cubic meters, or 100 square meters, floor space 2.44 meters tall inside the building. So this 5 liters per minute divided by 2,000 liters per minute, you get a default attenuation factor of 1/400 of 0.0025. In Hawaii, in our vapor intrusion guidance, originally published in 2005, the most current version is 2012, we come up with a little bit less conservative attenuation factor. We assume a vapor entry rate of 4 liters per minute, slightly less than they were assuming in California, and assuming an indoor air exchange rate of 4,000 liters per minute, or twice as much as they were assuming there. This should make sense. In Hawaii, people will leave their windows open quite a bit more than in California, plus year-round. So the default attenuation factor for for Hawaii is 1 over 1,000, or 0.001. So about a little bit more than twice as much attenuation of vapors as they intrude and mix into a building, indoor air. So method 1, it's been again used as the basis of US EPA's original vapor intrusion guidance published in 2004. It's very well studied by building radon experts, and especially ventilation and energy consumption experts. The models are based on a combination of field studies and empirical data, so these aren't theoretical. It's not a theoretical approach. It's just models based on actual field data, or calibrated field data. And again, it's used as the site-specific default approach in US EPA and California DTSC's vapor intrusion models, as well as several other states. Method 2 for developing subslab attenuation factors. This seems intuitively probably more simple, but you collect a sample of indoor air, and then collect a sample of the vapors under the building, test them for targeted VOCs, and the ratio of the concentration of the VOC in indoor air versus subslab soil vapors is your attenuation factor. This approach intuitively seems a lot more direct and accurate. Instead of attempting to estimate vapor entry rates and indoor air exchange rates, just simply test the indoor air, test the subslab soil gas. US EPA and others have put together a database of hundreds, actually over 1,000 homes and buildings, mostly in the northern and central part of the US. Most of the data was compiled in the early 2000s, and based on this data they calculate generic subslab attenuation factors based on statistical evaluation of the database. The draft document was most recently published in 2012. It subsequently received extensive public comment, including from our office. They're questioning some of the conclusions made in the reliability of the data, which we'll talk about in a minute. So here's a graph just summarizing the basis of US EPA's vapor intrusion subslab attenuation factors derived from the database of method 2. On the left is frequency that the attenuation factor was calculated for the buildings. On the bottom of the graph is actually the subslab attenuation factor. As you go to the right, increasing number up to 1, the attenuation factor is more conservative. So attenuation factor of 1 means they saw the same concentration of the VOC inside the building as it was in the subslab soil gas. Then to the left, the lower the number, the less conservative the attenuation factor. Now the median value they calculated or measured from their database is 0.003, 1 over 300, which is very similar to the values calculated based on method 1 approach for looking at attenuation factors. We're looking at the ratio of the vapor entry rate divided by the indoor air exchange rate. So that number, it seems reasonable. However, with the same database, in order to be more conservative, the idea was to be more conservative. They looked at the calculated 95th percentile upper confidence level for the subslab soil gas attenuation factor directly from the database of 0.03, or 1 over 33, so 10 times more conservative than the median attenuation factor developed from the database. California DTSC quoted an older version of the database document, and as a second default subslab attenuation factor, they recommended using a factor of 0.05, or 1 over 20, for just a 20-fold attenuation. So again, much lower assumed default attenuation of vapors as they intrude a building than based on the original method used. So under method 2, again, the default attenuation factor 0.03, 0.02, I've seen 0.01 used by other agencies, or 0.1 actually. It's been proposed for screening purposes. It's currently favored by some, but I would say not all, US EPA regulators. Now the problem again is that your resulting subslab soil vapor and groundwater screening levels based on this method can be 20 to 30 times or even 100 times lower than screening levels published by states based on the method 1 approach. So it's probably a lot of people listening to this webinar would know this can result in especially groundwater screening levels in the single digits of parts per billion levels instead of several hundred parts per billion is common using the method 1 approach for screening levels for groundwater. So what happens is a significantly larger number of sites get flagged for potential vapor intrusion risk. Many of these sites are left in bureaucratic or technical limbo because they're considered low risk or low priority, and whether or not vapor intrusion is actually impacting indoor air is typically irresolvable due to very low levels at the same VOCs detected in indoor air that could be within natural or indoor source background concentrations. So what ends up happening is this imposes a significant legal and financial burden on property owners and responsible parties. And that just from studies where we looked at more detailed subslab soil gas and indoor air data, the default attenuation factors used based on the 95th percentile upper confidence level, like 0.03, seemed excessively conservative for much or most of the U.S. So is there some additional health risk from this? Or do we really need to consider these very low or very conservative attenuation factors? Here are just some potential health risk symptoms: headaches, high blood pressure, heart problems, diabetes, dermatitis, arthritis, asthma, depression, anxiety. So is this caused some TCE? Well, no, these are actually health risks or symptoms and problems caused by stress. So semi-joking here, but in reality, these having your property flagged for potential vapor intrusion can cause a lot of problems, which would result in a lot of health issues. Just because it becomes very difficult to sell your property or refinance to redevelop your property. So the first problem with the database that popped up immediately is one size definitely doesn't fit all. So most of the data in the US EPA database was from cold areas of the country, the Northeast and the North Central states. So straight away the application of data from these areas and potential vapor intrusion risk to a place like Hawaii, where it's actually been pushed in the past, becomes very questionable. The majority of the indoor air samples were also collected from basements, so the ventilation of these areas is questionable, and that's where the dungeons part of our title comes from. One thing, however, is the indoor air data was within potential background from indoor sources for 80% roughly of the buildings. And when we first saw this was a good sign. So vapor intrusion wasn't a significant issue as far as impacting indoor air well above ambient levels just from indoor and outdoor sources for most of the buildings, even though the focus was on sites where vapor intrusion was clearly considered a potential concern. So that was good news. But the problem was that most of the data in the database isn't usable to calculate attenuation factors because you can't tease out potential impacts to indoor air from indoor or outdoor sources. Another problem is that it assumes a worst case scenario based on heating and a high vapor flux year round in the house. When you assume a high vapor flux, like 5 liters per minute every day throughout the year, that pretty much requires that the building be heated throughout the year. So that's the dragon part of our title. It's a dragon living in the attic, apparently. And then combine this, the use of combined minimum indoor air exchange rate and then a maximum vapor intrusion rate is highly questionable. That's where we refer this to a pica house. If you're not familiar with the term pica, a pica child is someone who eats dirt and everything they get their hands on. So they have very high health risks from this. Usually dirt is the least of their problems. So we were referring to one of these, a house that somehow had a very high vapor flux rate up through the floor, but very minimal indoor exchange rate as far as air leakage into the house from the walls and the roof, as a pica house, kind of a vapor-eating house, and a mystery. So the problem with this idea we'll talk about in a minute is that rates are positively correlated. As your indoor air exchange rate increases, then your vapor entry rate increases, and vice versa. So if you can't really assume a high vapor entry rate and a low indoor exchange rate. They're always going to be positively correlated. They're part of the same issue of building leakage. Still, it was an understandable approach when starting out to put the database together. We all used it, all thought about it quite a bit. But another problem that pops up, this is just quoting from California EPA's 2011 vapor intrusion guidance, among others, is that the default attenuation factors assume that the subsurface is reasonably homogeneous or uniform. Well, that's probably the biggest problem with the database right there. If you look at it in detail, out of the 1,000 or so buildings included in the database, in almost all cases they relied on a single subslab soil gas sample to calculate the attenuation factor for individual buildings. The maximum I noticed was around 3 samples for other structures, so very minimal. If you think about it just for a single slab, say at 100 square meters or so, there would be thousands of potential 1 liter vapor samples underneath that slab. So the representativeness of a single sample randomly collected beneath the slab would be highly questionable as far as it being related to potential impacts to indoor air. And as we'll talk about in some future webinars, as we discussed in our paper in more detail, as you increase the number of soil gas samples collected beneath the slab, then you start seeing more and more heterogeneity, especially say when you look at high density vapor pen studies or passive sampler studies. The more samples you collect, the more heterogeneous the vapor plume is revealed. So you can see a lot of spatial variability in vapor plumes due to source area heterogeneity, soil type, moisture, preferential pathways, air movement, and these types of issues. Oops. You collected a soil gas sample and the concentration beneath the slab was 1 milligram per liter. In this case you have 1 inside the building, 1 beneath the slab, so you would think your attenuation factor is 1. You're getting no attenuation of vapors inside the building. So where you collect the sample makes a huge difference in the estimated attenuation factor. And to make matters more complicated, in most cases you have no idea whether the vapors are actually intruding into the building. So the potential error in the estimated attenuation factor for any of the buildings included in the database isn't quantifiable. So implications for a database are pretty huge. If the accuracy of individual subslab attenuation factors is unknown, then the error in the extrapolated generic attenuation factors, like the 95th percentile UCLs, again, is similarly, it's unknown, it's not quantifiable. So really the database, although useful maybe for qualitative purposes, isn't technically defensible for development of generic attenuation factors. So one important thing is you can't fix this by statistical analysis of the database. And one note again was that the median value subslab attenuation factor calculated for the database was again similar to method 1. So something is useful with the database, but the error is unknown at this too, and we don't really explore that in detail in the paper that we published. If you want to read a really good book on databases and when you can and can't trust them, then we'd recommend the book The Signal and the Noise by Nate Silver. We actually reference that in our paper. So it's important to understand a statistician can't fix a bad database for you. Just for other examples, imagine if you collected a survey of ages or weights and then found out later that an unknown number of the people that you surveyed lied. So what can you do with the data? Well, not much. Or let's say you used a field PID to collect data on VOCs in the field, but then you later found out the PID was malfunctioning. You had no idea what the error was. Or you sent a bunch of samples to a laboratory, and then the laboratory said, well, our equipment malfunctioned and we don't really know how much error there is in the database, in the data that we sent to you. So what can you do with the data? You can't really fix that with statistics. You can't estimate means or 95th percentile UCLs. There's not much you can do. You don't know what the reliability of the quality is, so you have to start over. So really we're back to method one. It's the most defensible method to estimate subslab attenuation factors. And again, this is where you look at the estimated vapor entry rate for a building on an annual average and an annual average indoor air exchange rate. Well, a great paper was published as we were writing our paper by Sung et al. In 2014. The title of the paper was Quantifying the Influence of Stack and Wind Effects on Vapor Intrusion, and the reference is given in their paper. So what Sung et al. Did was they used well-established building leakage models, again used by building ventilation and energy consumption engineers, to estimate daily changes in indoor air pressure. That's the delta P on the left, based on building design and climate data for that specific region of the U.S. This delta P, or the difference between indoor and outdoor air pressure, is the key parameter in the US EPA's vapor intrusion model. So they used the building leakage models and then fed this delta P into the US EPA vapor intrusion model, and they were able to generate daily vapor entry rates. We look at the daily change throughout the year. And based on this, in addition to the indoor exchange rates, then you could calculate a daily subslab attenuation factor. Let's look at their daily vapor entry rates in more detail. So here, using their approach, you can calculate daily, seasonal, and annual average vapor flux rates, vapor entry rates, based on these building leakage models. So in this graph, the modeled vapor entry rate in liters per minute is shown on the left. Along the bottom of the graph is the days per year, with 1 being January 1st, 360, 365 being the end of the year. So as you can see from the graph, starting in the first of the year during the winter, the vapor entry or vapor flux rates tend to range between 2 liters per minute and 5 liters per minute during the wintertime when the building's heated. And heating of the building is driving that vapor flux. As you move into the spring, it's less heating, and also the model takes into account some wind effects and such for this part of the U.S. You see the average daily vapor flux rate starts to drop rather rapidly. By the time you move into the summer, the average vapor flux rate when the home is being cooled, in this case just assuming leakage through doors and windows, the vapor flux rate actually drops down close to 0, but ranges up to 2 liters per minute. So even the 2 liters per minute, so the worst case vapor flux rate during the summertime, this is driven almost entirely by, or it is driven entirely by wind effects. Moving back into the fall, as you start to heat your homes again, the vapor flux rate on a daily basis starts to increase until you're back into the wintertime. So the worst case scenario vapor flux rate of 2 to 5 liters per minute. One thing to point out is during the summertime, or at least when the building is being cooled with open doors and windows, if the wind isn't blowing, then the pressure differential inside and outside the building is 0, so the vapor flux rate would be 0. Also, if the building is being air conditioned, then air conditioning would typically overpressure the bottom floor of the building, and this would negate vapor intrusion. You could actually force indoor air into the subslab soil space. You have vapor extrusion. Now, we don't go into this in detail in the paper, but I think I've seen several cases where you have very high concentration of VOCs just a few feet beneath the building slab, but when you test the soil gas samples immediately beneath the slab, you find very, very low levels of the same target VOCs. And it's definitely way too low to be related to biodegradation. But if you look at the buildings during these periods of being air conditioned, what you're probably looking at is indoor air that was forced into this down through gaps and cracks in the floors and into the subslab space. So what we can do with this, with Sung et al.'s model, is have an expanded method 1, but we can assume default vapor entry rates for heating days, or days when the building is being heated, versus cooling days. So a heating day, if you look at some of the building ventilation engineer designs, they assume a building is being heated when the outdoor mean temperature is less than 65 degrees. So we can assign a worst case default vapor entry rate of 5 liters per minute. Again, this is per 100 square meters of floor space for days when a building is being heated. For days when a building is being cooled, when the mean temperature outdoors is greater than 65 degrees Fahrenheit, we can assume a default vapor entry rate of 2 liters per minute. So we have good climate data for across the U.S. So we know how many days per year the temperature is below or above 65 degrees Fahrenheit. So based on this, then for any part of the U.S., we can estimate an average vapor entry rate for a building based on the number of days that are below 65 degrees Fahrenheit versus above 65 degrees Fahrenheit, as shown in the middle box there. So we can develop climate-specific annual average vapor entry rates for any part of the U.S. One thing to note is that in the Mediterranean climates, which is essentially the central California coastal area, we assume a mean temperature of 55 degrees Fahrenheit as a cutoff when buildings are being heated or cooled. If you've ever been in San Francisco in the summer or the winter, then you can appreciate that. Most people, the residents there, leave their windows open even when temperatures drop down into the mid-upper 50s. And that explains also why along coastal California you tend to have a higher indoor air exchange rate than you might expect given the mean annual temperature. So you can take this information then. We have a way to calculate average vapor entry rates annual for any part of the U.S. Combine this with published estimates of annual average indoor exchange rates. Then we can calculate the default attenuation factors for subslab soil gas indoor air for any part of the country. So let's look at that in more detail. Well, most of this work's already been done. This is the climate zone map published by the Commercial Buildings Energy Consumption Survey. They split the U.S. up into 8 different climate zones, noted by the different colors and the very small numbers here. We elected just to split the U.S. up into 4 basic climate zones based on how many days per year really the temperature is below or above 65 degrees Fahrenheit. So region A, no big surprise, the northeastern U.S., Rocky Mountains, and the north central states we define as the cold area, including Alaska's included in this, the cold region. Region B1, the southeast and southwestern U.S., a little bit warmer than region A. The average temperature is above 65 degrees Fahrenheit for a longer part of the year. Region B2 is coastal Oregon and Washington, which from a heating, ventilation, energy use standpoint is real similar to the southeast, believe it or not, and also from a vapor intrusion risk standpoint. Region C is the Mediterranean central coastal area of California. Again, there we used a cutoff of 55 degrees to estimate how many days per year a building might be heated versus cooled. Region D is the tropical climate zone. This includes the south tip of Florida and also Hawaii. So you can see in the bottom part of this diagram we looked at data for climate published by NOAA and other organizations and came up with an estimate of the number of days when the temperature in each one of these regions on average was below or above 65 degrees Fahrenheit. And then we use this to calculate average annual vapor entry rates. So the next slide we give a summary of the average number of heating days per year for each region and the average number of cooling days per year. You see the default vapor entry rates assigned to each one of those 5 liters per minute for heating days, 2 liters per minute for cooling days. So based on this we can calculate a weighted annual average vapor entry rate for each one of the regions. And again, for the regions A, B, and D, we're assuming a cutoff of 65 degrees Fahrenheit Mediterranean areas in region C, we're assuming a cutoff temperature of 55 degrees for heating versus cooling. So you can see the number of heating days decreases as we go from region A to region D, whereas in tropical areas it assumes 0 heating days per year. So the weighted annual average vapor entry rate also is highest in region A, 4.5 liters per minute, very close to that maximum of 5 liters per minute. And then this drops down to 2 liters per minute for region D in tropical, where it's based entirely on the default vapor entry rate for cooling days. So next we can look at published indoor exchange rates for each one of these regions. In region A, we assume a default indoor exchange rate of 0.35 times per hour, and that's within measured field data for that area. Also, it's the minimum ventilation rate for residences required under building permits. If you assume a 100 square meter building with a total volume indoors of 244 cubic meters, this is the default in US EPA's vapor intrusion model. This equates to a default indoor air exchange rate for region A of 1,423 liters per minute. Region B, this is the southeast and southwestern US and also coastal Oregon and Washington. The default indoor air exchange rate increases slightly to 0.5 times or half a time per hour. This means the air inside the building is getting exchanged half of the air is getting exchanged per hour. So you get a complete indoor air exchange every 1 hour. This equates to a default indoor air exchange rate, again for this a building 244 cubic meters in volume of 2,033 liters per minute. Region C, Central Coastal California, the default indoor air exchange rate, again based on published data, increases up to about 1 time per hour. So your default indoor air exchange rate in liters per minute doubles from that of region B to 4,067 liters per minute. Now in the tropical areas, southern Florida and also Hawaii, we don't have a lot of indoor exchange rate data, so we assumed at a minimum it's equal to region C at 1 time per hour. It's probably much higher than that. So I like to joke with my friends on the mainland, especially at this time of the year in February. I haven't closed my windows in about 10 years, and I've only lived in the place I am now for 10 years. So we get very high indoor air exchange rates here. So we assume the same default indoor exchange rate of 4,067 liters per minute for region D. So we have default vapor entry rates, and now we have default indoor exchange rates for each one of the regions. This table just summarizes that. So now with these, using that same method for attenuation factor, the subslab soil gas attenuation factor is equal to the average vapor entry rate divided by the average indoor exchange rate. And you see those calculated now for each one of the regions. At region A, that the cold region of the US, there's that number again they got in the database, 0.003. So there's some agreement there, and that's actually where most of the samples of the data in the US EPA's database were collected, from region A. So that seems to be correct. Region B, for the warm areas of the US, a slightly lower attenuation factor, 0.002, or a 500-fold attenuation. So you're getting slightly greater attenuation of vapors because of an increased indoor air exchange rate and a decreased vapor entry rate in region B. So this makes sense. People keep their windows open more often in the southwest than they do in the northeast. They're also heating the buildings and homes less during the year. Not a huge difference, but definitely noticeable. Region C in the Mediterranean, central coastal California, again your vapor entry rate's going down, your indoor air exchange rate is going up. Calculate a subslab attenuation factor 0.0008, or roughly 1 over 1,000, which is the default that the Regional Water Board in San Francisco Bay Area with California EPA assumed in their subslab soil gas attenuation factors originally, roughly 0.001 or 1,000-fold attenuation. Region D, tropical area, southern Florida, Hawaii, similar. Again, your vapor entry rates has gone down to the minimum, which is still conservative, 2 liters per minute. assume the same into-air exchange rate. It's probably too conservative, but now we're looking at a subslab attenuation factor of 1 over 2,000-fold dilution, if you want to call it that, attenuation of vapors after intruding into a building, for a factor 0.0005. So now we can go back to the original map, this climate map that was already been published, and assign now in this figure we're calling these vapor intrusion risk regions. We have region A, the cold region, region B, 2 in this diagram, warm in the southeast, or the coastal areas of Washington and Oregon, and then region C, central coastal, California, Mediterranean, region D, southern Florida and Hawaii. And you can see down below where we've assigned the default subslab attenuation factor to each one of these regions. So now it starts to make sense, where you see a difference in vapor intrusion risk between some place like upstate New York versus coastal California, or someplace like Hawaii. The difference isn't that great, and in reality it's probably a lot greater, but the difference between the default attenuation factor 0.003 for region A versus Hawaii 0.0005, it's only a 6-fold difference. And in reality, the vapor intrusion risk in Hawaii is, in southern Florida, it's probably much less, much lower than that in compared to the colder parts of the U.S. So that's it. That's really the gist of the paper, is being able now to come up with more usable and realistic attenuation factors for different regions of the U.S. based on climate data and based on the original approach used in U.S. EPA's vapor intrusion guidance document. So again, the database is worthwhile to compile. We certainly would have done the same. We've been looking at it for 10 or 15 years now, but when you look at it in more detail, and based on the growing evidence of vapor plume heterogeneity, then using the database to estimate generic attenuation factors, this isn't technically defensible. Although again, I said before, the median looks like it was in the right ballpark. So just that tells you something about vapor plume heterogeneity. Is some large enough fraction of the samples of the data included in the database do appear to be accurate. So vapor plumes are heterogeneous, but not nearly as heterogeneous as, say, contaminants in soil. So now we can compare estimated vapor flux rates or vapor entry rates to indoor exchange rates. It's still the most defensible method for estimating subslab attenuation factors. Again, these attenuation factors get pulled into screening levels for not only subslab soil gas, but deeper soil gas, and in particular groundwater screening levels for vapor intrusion. So the thing this allows us to do now, as we highlight in red down here, is the screening levels now we believe are much more realistic and more usable. It allows us especially to screen out low risk vapor intrusion sites, especially where VOCs in their single digit part per billion level, there's really no field evidence of significant vapor intrusion impacts from such low levels of VOCs in groundwater. Most of that concern was being driven by the database, which we now know wasn't completely accurate. So using this back to method 1, and now we split it up into regions in the U.S., allows us to quickly screen out these lower risk sites and get them out of the bureaucracy and focus our resources on the truly high risk sites. Now, the next part would be how to use subslab soil gas to screen sites for potential vapor intrusion concerns. And there is enough data out there, especially when you look at more detailed field studies, to use the subslab soil gas samples from the center of a slab as worst case scenario for estimating vapor intrusion concerns. So in these areas is where you'd expect the highest concentrations of VOCs to accumulate. Either that, or if you look in more detail, you might want to move toward the downwind side of a slab. If you're in some place like Hawaii, we have very persistent, say, trade winds during certain parts of the year. Or you could focus on areas of the slab where you suspect a specific source might be located beneath. So that's where you would collect your soil gas samples to evaluate for potential vapor intrusion concerns. Again, those soil gas screening levels will be based on the attenuation factors we just discussed for each one of the regions, and along with your target indoor air screening levels. Here's just an example of screening levels published by Department of Health. This is for TCE, residential chronic exposure. In our guidance, we currently assume a vapor entry rate of 4 liters per minute, which based on the paper that we just published is probably at least 2 times too high. But sticking with that, we assume an indoor exchange rate of 1 time per hour, which equates to 4,000 liters per minute roughly for the default building size. This gives us a subslab soil gas attenuation factor of 1,000 that we include in our current guidance. So in the case of TCE, the risk-based concentration for residences is, in our guidance now, is 1.2 micrograms per cubic meter. Multiply this by 1,000, that gives us our subslab soil gas action levels. We call them here 1,200 micrograms per cubic meter. Based on a combination of models and field observations, we assume a separation distance of 10 feet, then a subslab soil gas concentration of 1,200 micrograms per cubic meter would equate to a concentration of TCE in groundwater of 610 micrograms per liter. So that's our groundwater screening level for TCE. So what this means in the field is that we wouldn't expect to see TCE in soil gas greater than 3 meters or 10 feet from the water table to exceed 1,200 micrograms per cubic meter if the TCE in the groundwater was equal to or less than 610 micrograms per liter. So we haven't seen any field data to break these action levels yet, or to discount them. They appear to hold up very well. So we would use these screening levels to initially usually screen out low risk sites and focus on the higher risk sites where we have higher concentrations in groundwater or soil gas. So based on this review, we just went over Hawaii's vapor intrusion action levels, for groundwater, soil gas, are overly conservative by at least a factor of 2. So we assume in our models that the vapor flux rate is, we assume a very high vapor flux rate, 4 liters per minute. So we may or may not fix that in future guidance. At this point, it's a factor of 2 isn't that unreasonable for a safety margin. So our subslab soil gas action levels appear to be adequately conservative with a nice buffer to them. Same thing with the groundwater intrusion screening levels. They appear to be holding out well. One thing, if we suspect a contaminated soil source, we usually go straight to soil gas instead of making decisions based on the soil data. That's also discussed in EPA's guidance documents as well as California's. Anytime we've seen unexpectedly high concentrations of VOCs in shallow soil gas compared to groundwater data, whenever we looked in more detail, we usually find a nearby soil source that's causing the high soil gas concentrations. Or if we look at more detail, the groundwater data, put in more wells, we realize that the concentration of VOCs in the groundwater, especially in the very shallow groundwater, is much higher than expected. A big issue for Hawaii is most of the buildings here are air conditioned much of the year. This is going to negate significant vapor intrusion risk for much of the year, or for most of the buildings here, due to overpressurization of the lower floors. But still, our screening levels assume the buildings aren't air conditioned, and that cooling ventilation would be through open windows, maybe open doors, and that the winds are blowing, and that would drive depressurization of the building in a minimal 2 liters per minute vapor flux per 100 square meters floor area. So that's too conservative for most of the buildings here, but that's what we use in our guidance. For more details, you can refer to section 13 of our technical guidance manual. Again, we don't plan any updates in the future. Some of the other vapor intrusion guidance, again, we talk with a lot of people in different states and in the EPA. Several states, some of them are using this approach, and they've always questioned the database approach, but we've been talking with them also about potentially using the attenuation factors in our paper, when they would work, when they wouldn't. Another thing some states are doing is taking a closer look at groundwater screening levels. This tends to be a huge issue when you have a low concentration of VOC plumes, especially chlorinated solvents, under a very wide area, especially under a big residential or commercial area. And it underlies hundreds of buildings or homes. So we want to be able to screen out the low-risk sites very quickly, get them out from under the bureaucracy again, and be able to focus on the high-risk sites. So several people now are looking at paired groundwater and shallow soil gas data to confirm the adequacy of groundwater vapor intrusion screening levels for different parts of the U.S. Let's get back to. So what's the next step? I think now that we have a better understanding of attenuation factors and related screening levels and such, the next step is to get better data, more reliable soil vapor data. One of the biggest problems with soil gas samples is probably that they're just too small. They're too small to overcome random heterogeneity of VOC concentrations in vapor plumes at the size that the sample is collected. Now this can be accomplished in two ways. One is by collecting a larger number of samples. I think a better way to go, a certainly needed way to go, is to collect larger volume samples. In this slide we're depicting the area covered by soil vapor samples of different volumes. Just as an example, we're assuming that the vapor is coming from the first 15 centimeters, 6 inches of fill material underneath of a slab, and that the fill material has approximately 20% air-filled porosity. Now to put this in perspective, a 100 meters squared, 1,000 square foot area floor space under this scenario would have over 2,000 liters of vapor in the subslab fill material. Now looking at this, you can see the 50 milliliter sample only covers a few centimeters of floor space here. So what's the chance of that sample being representative either of the vapors around that sample, or even if you collected 5 or 10 of these samples across this entire floor, what's the chance of those samples be representative of the average concentration of vapors beneath the floor? My guess would be pretty slim. It would require that the vapor plume be incredibly homogeneous. The 1 liter samples, which aren't that much larger and are far more common, still aren't that representative. You can see a very small footprint covered by the 1 liter sample. 6 liter samples, it's a limit of sumocanisters, getting a little bit better. They're still fairly small. You need a lot of these just from an instinct standpoint to get a representative idea of concentrations beneath the slab. This next slide shows figure shows a 50 liter sample. So this is the footprint of a 50 liter sample underneath of a slab. So now we're getting large enough where I would think intuitively that we probably can overcome small scale random heterogeneity of VOC concentrations in vapor plumes beneath the slab. Now once you get above 6 liters, now you're looking at using sorptive tubes to collect a sample. And as far as I know, this hasn't been done before, so we're just speaking hypothetically here. Here's the footprint of a 100 liter sample of soil vapor in theory collected beneath the floor. So now we're getting large enough. My guess is we're able to overcome random small-scale variability of VOC concentrations beneath slabs or in vapor plumes in general. So now we're getting close to something we can make a decision on. Well, how can we accomplish this? There are actually two ways. One way would be to collect more and more typical subslab soil gas samples as we've been doing, just more of them. Another way would be collect larger volume samples, which I think is the way to go again. First thing we need to do is step back and think about what we're actually looking for. This is what we started doing for soil about 10 years ago now in Hawaii. And we do this by designating what we call decision units. A decision unit is simply an area or a volume of a media, including soil vapors, where you want to determine the mean concentration of the contaminant present. So in this case, for this building here in the slide, the decision unit might be the center 1/3 of the building, where you may expect the highest concentrations of VOCs in a vapor plume to be present. Now, if you want to get more information on decision units and their use and intent, then you can refer to the Department of Health guidance and ITRC guidance on incremental sampling. So in this case, let's assume our decision is the middle third of the building slab. We want to determine the mean concentration of VOCs and vapors underneath the slab. Well, now in this example, I'm depicting 9 100-liter soil gas samples collected immediately beneath the slab. So you can see we get good coverage in this area. And now give me this kind of data. This is the type of data I can make a good decision on, confident decision regarding vapor intrusion risk to this building. Now, again, this is hypothetical. I don't know that anyone's ever done this. We may try it in a field study here in the next year or so. Now someone is inevitably going to bring up, well, yeah, you're just getting the mean concentration. What's the maximum concentration of TCE, let's assume in this example, beneath the building slab? And they may try to determine this by collecting 50 milliliter samples or 1 liter samples and claim this is why we need to be collecting smaller samples so we can detect the maximum concentration. Well, think about it again. Within this small area here, there's well over 1,000 liters of vapors in the first 6 inches of fill material beneath the slab. So what's the chance of you identifying the maximum concentration of TCE or some other VOC by randomly testing 1 or 2 or 3 or 4 or 5 or whatever of those 1,000 plus potential 1 liter samples? Well, it's very low to nil, especially if you're trying to do it something like a 50 milliliter sample. Well, now you're looking at probably tens of thousands of potential 50 milliliter samples beneath this area of the slab that you could test. So the chances of finding a maximum concentration is nil, and in the end it's unimportant. If you want to know the maximum concentration of TCE in the vapors beneath the slab here, it's very simple to tell you. It's 100%. As you start looking at smaller and smaller sample volumes, sample sizes, eventually you get down to the molecular level and you'll find 100% TCE. So the maximum concentration is really a myth that we were stuck with for a long time with soil, and I think we're still stuck with that in some places for soil gas. What we want to know is what's the maximum mean concentration of VOCs in the vapors beneath the building slab within designated decision units beneath that slab. And that's really where we need to head. So that's it for this webinar. So thanks for attending and listening in. Thanks for all the comments over the past several years. Keep them coming. My contact information, email address was on the first slide. Feel free to contact us anytime with any ideas or suggestions. The next Hazard Evaluation Emergency Response HERE webinar is going to be on March the 11th, 2015, 11 a.m., 12 p.m. Hawaii time. In this case, we're having our other two co-authors, Mort Smith with Cox Coven, Harry O'Neill, Beacon Environmental. We're going to be showing us really detailed data from their soil gas, active and passive soil gas samples, looking at vapor plume heterogeneity, and maybe talking about why you need to collect more samples and potential options for collecting larger volume samples. So again, thanks for joining in, and thanks for all the input in the past. Aloha.